watching live. That's me.
Hello, everybody. I think this is the first live streaming Science Cafe that I've been a part of. And so I'm going to wing this a little bit, but I feel like we're pretty good and ready to go. Chiefs game is over, if not officially, in all practical. For all intents and purposes, it's over. We just finished watching it. So people should be coming in. No excuses now. Have a live audience here of 2, my wife and my son. And so if there's any comments or questions or whatever during the middle, they will be screening. So I'm assuming if it's mean stuff, they'll tell me later. They may not tell me during the middle. I'm not sure if anybody else from Science Cafe has any opening remarks or anything. So that's kind of why I'm just killing a few minutes here. My son's making a funny face.
Science Cafe says, looking forward to learning more about climate change.
All right. Well, here we go. You're in the living room of the Dixon household. Sit down. So I'm going to go dad mode every now and then, and if I do, I'm not talking to you, I'm talking to my son. I guess I just want to start by thanking the Science Cafe folks for still trying to keep some of these things normal and put this together. I enjoy giving these talks. I enjoy talking to groups. I don't get to do it as much these days. I'm not in the classroom, and so I jump in any opportunity that I have to speak to groups, especially about science. And tonight we're going to talk about climate change. When I was first asked to do this, we had no hints that a pandemic was coming. I think I had a few months, maybe it was late 2019, I started planning for this. And I knew pretty much what the audience was going to be. It's the group that always comes to these Science Cafe events. And so since then, when we rebooted and decided to go online, I didn't really know which direction to go. So I'm assuming that it's mostly the same overlap of groups that would be here live. But I've also put in some stuff for a much larger audience. Not necessarily larger in number, but larger as in coming in from a broader set of distances. So I'm going to try to hit a lot of the main points. I'm sure I won't hit everything that most of you are interested in hearing, but I'm easy to get a hold of. These are my contact information, email address, and Twitter, and I'll put them up at the end. Feel free to send me any questions you have. And anytime we talk about something that has political implications, a good scientist, anybody I think with, got their ethics in the forefront here, will reveal any conflicts of interest. And I'm here to say I have 0 conflicts of interest related to the issue of climate change. My research, I'm a climatologist. I have a bachelor's degree in meteorology and both my graduate degrees in geography and climatology. I've done tons of research on lots of weather-related issues. Climate change is related to almost everything I've ever studied, but I've never been a climate change scientist per se, as in I'm not out to study simply climate change for the sake of studying climate change. I've never received any sort of external funding related to climate change, so I have no vested interest in there being one particular answer or another with any of the things that I'm going to show you here. My interest is in following the science and being as efficient as we can and informing the public as clearly as we can whenever we discover new things. And so I'm going to start by explaining a little bit about how science works. A lot of people learn about the scientific method in school, and maybe they go on and take some classes in college. But even advanced science courses don't do a great job of drilling in what it's like to be a scientist. You have to take several courses and really experience this stuff to realize it's frustrating, and it doesn't happen quickly, and you almost never prove anything. It's about compiling evidence. And so scientists, in the interest of always being completely open and sharing what they know and what they don't know, we talk about uncertainty. Well, in everyday language, if you're uncertain, you don't know what you're talking about. And so people shouldn't listen to you. But in science, uncertainty is very important. It helps us narrow in on the places to study further to understand better, knowing that you can never understand completely. And so I've shown a few examples here, bullseyes, you might recognize from an intro-level science class that talks about precision versus accuracy. And of course, the bullseye on the left is kind of the ideal situation where our little red dots represent the samples of the science that we're studying or the topic that we're studying. In this case, we are accurate and we are precise and we are consistent, in other words. So if you're going to make a prediction based on these observations, you feel pretty good that your prediction is going to be accurate. And then you compare this to the next bullseye, which is nearly useless. None of them are close to the middle. They're not close to each other. If I asked you to guess where the next observation might land, pretty much anything is possible. Or over here, we feel pretty good that we would be able to guess approximately where the next sample might fall. Then we have one like this. And this is where the public's understanding of science really starts to fall apart. In this case, we're not accurate, but we are precise. We are consistent. That systematic consistency is actually very helpful in science. I can make a prediction here that is useful because I know the approximate distance from the target that we're aiming for, and I know how consistent they are among each other. And so if this is the way that your samples are falling, you know quite a bit. You can make valid predictions. You may not understand enough details to know why your model is wrong, but you at least can make useful predictions. So this is still good. This is best, so to speak. This is a really close second. And this is quite helpful. This is when you feel good about understanding the processes, the science at hand, whatever the topic is. You understand generally what's going on. The problem is the samples are not very tightly packed. You know that if you had 1 million samples of whatever this is, eventually they would center in on the bullseye. But you never know quite what that next one's going to do. So there's just lots of variability. And so this might be forecasting the weather in the Great Plains, for example. There's so many variables, dry air, terrain, and everything else, that you know generally what the answer is going to be, but the variability is so much that your precision is not so great. And I want to add here, science, depending on the science philosopher that you listen to, science is not in the business of proving things. It is essentially testing ideas. And over a long time, if you have an idea that cannot be destroyed, that cannot be discredited, then that idea becomes really well respected. It becomes a theory. And that's how you prove something, is by failing to disprove it. And so this Wile E. Coyote here has a little sign, if you can't read it, it says, "Gravity is just a theory." And so when I'm in class, I'll tell my students that I could do this all day, every day, for the rest of my life, and we haven't really learned anything new about gravity by me tossing this up. It took a long time to get here. The first thing that fell, the apple from the tree, so to speak, that hit Newton on the head, that didn't suddenly make him prove gravity. It was one sample. And then many samples later, we start understanding gravity. Well, if I toss this up and it fails to fall down right here, right now on camera, what happens then? Did we just disprove gravity? Well, probably not. There will probably be a lot of people studying the video and coming to my house and tossing this remote and trying to see if somehow gravity doesn't work as we thought it did in the Dixon household. More than likely, they're going to discover it was some problem with the Wi-Fi and everything's back to normal again. But we had to diverge and we had to spend a little time on this weird failing to fall remote control problem. Well, I think that's where we are right now in climate change. For the most part, we understand the big picture. But we've got these little remote controls every now and then that just don't quite fall, and we're having to diverge from the big steps forward and make sure that the foundation is good. And so I'm going to say a few things tonight about people that are throwing up arguments against climate change. And some of them, maybe they'll come across a little flippant because of the time we have or don't have. But I want to say there's nothing wrong with questioning science. That is the process of science. If everybody just agreed all the time, there'd be no progress in science. Or if it was, it'd be progress in the wrong direction. We'd be leading down trails that we hadn't fully investigated. So I'm not here to say that nobody should question the processes of science, but I am saying that if over time we continue to disprove your idea, maybe it's time to give it up. So with that being said, there is very little doubt, although there's always going to be doubt, that our climate is changing. And by our climate, I mean the globe, I mean the country, the state of Kansas, pretty much any scale, we're going to find a changing climate. And so these are data going back to 1880. These are average temperatures across the planet, over the land, over the ocean, for all the places that we can collect data, which is not every single place, but it's a pretty good representation. And what you see is a clear increase in temperature, especially in the second half of the 20th century, with no signs of slowing down. The gray line, the gray shading behind the black lines is the uncertainty. So that's the range of areas that are warming around the little black dots, which are the average values each year. So the uncertainty is important. Some years that uncertainty is greater, other years that uncertainty is very tight, which means our data agree. So these are areas around the bullseye tightly clustered, and these are those that have a little more spacing, which makes sense because they're way back in history when our instruments weren't as good. And then the red line is just a smooth version. If you look at it by season, it's warming in every season on average, but it's not warming at the same rate. And this is an important thing. The blue lines are early parts of the record, and the red lines are the later parts of the record, so it works out that it's going from cold colors to warm colors with time. And the spread is much larger during the cool season. So January, February, December, those are when you have the greatest warming. Really during the transitional season, spring and fall, the difference is still there. We're still warming, but we're not warming as dramatically as we are during the cool season. And then if you look at the U.S., still warming, not as consistently and not quite as dramatically. We had this big period from the 20s through about the 40s or 50s where we had a pretty warm climate over the U.S., and then we had a cool period through the 70s and the early part of the 80s, and ever since then it's been on track with the rest of the planet, been very consistent. But you see a lot more noise just because it's a smaller area. Anytime you have fewer samples, you're going to have more variability. And so these two graphs are the same that I just showed you. This is the globe, this is the U.S., just so you can see them side by side. Same pattern, but the U.S. is less smooth. If you look around the U.S. in terms of the spatial variation, not the temporal variation, it's not the same everywhere. Some places are warming very dramatically, in particular the northern latitudes. So we see the coldest parts of the planet tend to be warming faster, and the coldest times of the year tend to be warming faster. But if you look at the deep south, in particular states of Mississippi and Alabama, for a long time, they didn't have any warming. In fact, they continued to cool through the 60s, 70s, 80s, and part of the 90s. I grew up in Mississippi, and I remember 1988 was a really anomalously warm year. It was kind of when the rest of the U.S. really woke up and realized that climate change is probably a real thing, and Yellowstone was on fire. The South, that was really the only warm year that was quote-unquote unbearable or really unusual over my childhood. And it wasn't until about the last decade or so that this part of the country started warming. I think this is important to point out for a few reasons. Climate change has been cast as a political division of people that think there's climate change and those who don't think there's climate change. And these people are maybe more progressive or liberal, and these are more conservative or Republican or whatever. It is not that clean. But sometimes it pretends to be that clean because this very conservative part of the country wasn't experiencing any changes. And so you tend to believe what you see with your own eyes, and these folks had very little reason to believe it. Now things are changing, it's coming around, and I think we'll start to see some of those political divisions vanish as we move forward. Just for note, western Kansas is almost exactly the same as the U.S. average warming since 1901. And these data go through 2015, so it's actually a little bit warmer now, but still we're consistent with the rest of the country on average. Well, how do we know this? I could spend a long time. I could spend twice the amount of time I have tonight just showing graphs and data suggesting that climate change is happening in dramatic fashion. And so these are the common ones that you'll see. Sea level is rising around the world. The ice sheet in Antarctica, the total mass of ice is decreasing. The Greenland ice mass is decreasing. The extent of ice horizontally throughout the Arctic is decreasing. And there is variability. There have been some years where suddenly it expanded dramatically from the year before. But then it takes a couple more steps down. And over the long term, even of a decade or so, we're seeing decreases in ice everywhere around the globe. And there's so many other things that we can show that are not necessarily climate variables. For example, the onset of spring frost, the last frost in the spring and the first frost in the fall. Not everywhere, but most places that you look, certainly in North America, you're seeing an earlier last frost in the spring and a later first frost in the fall. Again, not every year and not every place, but on average, we're seeing a spreading of those two. If you look at animals around the world, the places where birds travel for winter, they're having to travel greater distances between their summering and wintering locations, and because habitat isn't always what they've evolved to expect in certain places or certain distances, they're having to travel much larger distances than they would expect biologically. And so it's becoming a real stress for a lot of species. Not all species. Some species, I'm sure, are doing as well or better than in the past. But on average, you're seeing a much larger spread of migration distances and wintering ranges. Here's an interesting one. This is the change in first leaf date. So if you're looking at, for example, like when the first bud pops out in the spring, or when leaves start to fall, turn colors in the fall. And what you're seeing is that in the northern latitudes, you're really seeing a change towards the warmer environment. And so your buds are coming out earlier than you might expect. Whereas in the southeast, it's happening earlier, actually. And that goes back to the graph I showed earlier in this presentation, where much of the southeast actually was anomalously cool for the last 30 or 40 years. And so these data do make sense with what we've been seeing, but across most of the northern U.S., and if you continue into Canada and Alaska, you see nothing but reds and oranges. These are maps of fish and lobster off the coast of the northeastern U.S. The light dots of green and orange are showing earlier habitat ranges of these animals, and as we move forward in time, the darker dots are showing up. We're just showing drifting north, right? As the water's warm, the habitats are moving to the north. We could go on and on with all sorts of animals in this scenario. And then, of course, the ubiquitous photo of a glacier, before and after. And sure enough, this is a glacier in Alaska, 1941 in the month of August, 2004 in the month of August. You have some variation in glaciers each year, but not much. Certainly not this much, not miles of glacier retreat. So this is something that is happening over a long scale and is pretty undeniable. Well, and then here's the take-home message. There really aren't many people left that are worth listening to, I suppose, that say that climate change isn't happening. The real argument now is, why is it happening and what is there to do about it? There's very little evidence that anything about climate change is being caused by anything other than people. So that's a verbose way of saying we're doing it. We are causing almost all of it. We are causing the part that we care about, that's for sure. And so this is CO2 as plotted over a very long time, thousands of years before present. In fact, 800,000 years before present. And what you see is there was a lot of variability. There were times when it was up and times when it was down, and there's all sorts of reasons about why that happens. And then, this is when humans emerge, and then you can see later when essentially we started mechanizing and had the Industrial Revolution, and then suddenly CO2 is off the charts, at least off this chart. Certainly much higher than you would expect given our history by somewhat relative recent standards compared to the rest of the history of the Earth. How do we know that? How do we know how much CO2 was in the atmosphere thousands of years ago? There's a lot of ways. And that's the good thing about science. If you can use several different methods and different data sources and arrive at a similar answer from different perspectives, it gives you a lot of confidence in that answer. So this didn't all come from one thing. The most common, though, that we are seeing are tree rings, which are not going to get you back 800,000 years, but they'll get you back 4,000 or 5,000 years, believe it or not. There's lots of species, not lots, a handful, maybe 6 or 8 species of trees that live thousands of years. And one of them is the bristlecone pine, mostly in California, east of the Sierra Nevada. So I actually took this photo on a field trip a few years ago. And this is a bristlecone pine. They live thousands of years. You drill through them, and you get a history of your climate in that location. There are also ice cores. You can drill down through the Arctic or the Antarctic and go much farther back into time. And what you're looking for is within the little gas bubbles, you're trying to see what kind of pollen is present, what kind of plants used to live. You do similar things with water analysis, isotopes of water in stalactites and stalagmites in caves. And so again, there's multiple ways of getting to this answer. And the answer is there's more CO2 now, and the temperature is warmer. Now, you can't always take one thing. It's not always about temperature. It's not always about CO2. It's not always about the fish swimming more to the north than they used to be. But if you understand the processes, then all of the other details start to make sense. And so a reminder of a greenhouse gas. A greenhouse is a thing that has relatively clear walls and a roof. The sunlight is able to pass through relatively unaffected. It heats up the ground inside. And when it heats up the ground releases long wave energy that's less intense and can't move back through the glass. So it traps the heat, so to speak. That's what CO2 and other greenhouse gases do. There are lots of other greenhouse gases. Here's CO2. This is the efficiency of greenhouse gases. Methane is 25 times more efficient. Nitrous oxide is 300 times more efficient. A lot of our fluorinated gases that we use in things like oxygen tanks for scuba diving and such, they're tens of thousands of times more efficient than CO2. But there's just not as much CO2. This is the amount of warming caused by each of these gases. CO2 is about 3/4 of the warming that we see. Water vapor is also a greenhouse gas. The warmer the air gets, the more water vapor there is. It's a positive cycle. And so I do want to say that there's evidence that CO2 used to be higher. I showed you a graph a minute ago where it was as high now as it had been in the last 800,000 years. Well, we think that hundreds of millions of years ago, CO2 was higher than it is now. The catch is there were still glaciers. It wasn't as warm necessarily then as it is now. By the way, it's also been warmer than it is now. So you can take these two things and say there used to be more CO2 and it used to be warmer. That's true. They just didn't necessarily happen at the same time. And the reason is you could have more CO2 a long time ago and it still not be as cool is that the sun was actually significantly dimmer hundreds of millions of years ago. And so the question becomes, technical difficulty. There we go. What's going on with the sun now? A lot of people want to say, well, that's just the sun. The sun is now getting hotter than it used to be, except it's not. The sun does go through cycles. We've heard about sunspots and their little flares of energy on the surface of the sun. And this is temperature in red. This is solar activity in blue. And what you've seen since about the 60s is that the solar output has gone flat and even started to curve downward. And so if we were accounting just for quote-unquote natural factors, which is a really dangerous word. Natural means a lot of different things to a lot of different people. But if we took out the man-made, human-made climate change, we would expect our temperature on Earth, on average, to be going down slightly over time. If nothing else, it'd be about constant, but probably going down a little bit. And we don't see that. And so it can't be the sun because it's going in the opposite direction that we would expect. I could spend a long time going through what about this, what about that, what about this. The what about game is one that is very hard to swat away. They're like flies. They keep scientists from making a lot more efficient progress because we're always trying to check the research to be sure that we can meet these whatabouts. And so one of the more pesky whatabouts is this graph. This graph is based on analysis that was done in the late 90s. It didn't show up until about 10 or 12 years later, and it was essentially pieced together by a non-scientist who was trying to make the point that climate change was a big hoax and it was a waste of everybody's time and so forth. And now it still makes the rounds. I think the person who made it may have passed away, but it still makes the rounds on various websites and social media. And the problem with this graph, one of many, is that it's outdated. and it's misleading. So I guess two of many. And the way that it's misleading, I already said it was outdated, right? It was from analysis, the way that we thought we understood some things in the 90s. The x-axis, the horizontal, is misaligned. It says these are years before present. There we go, years before present. But the end of the x-axis goes to about 1950, not to when 2010, which is when this would have been presented the first time. Also, this graph includes no actual observations of the climate. These are all proxies, which is fine, but if you continue to use proxies into modern times, into current day, the last 50, 60 years, your proxies become less reliable than the actual temperature data that you have. So that's a problem. And also, we learned a lot in the 10 or 15 years between when the data were first analyzed and this graph was first presented, things about how elevation changed over the time of all these ice cores that were collected. And by the way, this is a single ice core. This isn't even just like a single county-sized area in Greenland. This is a single ice core that was used to create this graph, and it's presented to show people that, oh, it used to be much, much warmer. Well, it did used to be warmer, just not that much, and more importantly, the change that we're experiencing now is quite alarming. And so after you correct all the errors in this graph, this is what you find. That yes, and these are thousands of years, and so you've got, 2,000 years here, 2 millennia. And so here we are in the year 2020, 2,020 years ago, year zero, so to speak. We've never been warmer than now. If you continue to go back, say 6,000 years or 8,000 years, yes, we have had some warmer periods. And we understand that. Nobody's arguing that. But it's this segment here that has us most concerned. Other whatabouts. If we have warming climate, how come we still have all this cold weather? Well, climate change is warming things. It's not totally eradicating winter. And in fact, in some ways, it makes winter seem worse. I guess it depends on your definition of worse, though. Is just being cold a bad winter, or is being snowy a bad winter? In this case, we had a senator, a U.S. senator, that brought a snowball from his state onto the Senate floor to claim that White House efforts on climate change were a waste of funds from the government because there was snow in his state. Believe it or not, if the climate warms in particularly cold areas, places that tend to get snow anyway, they're more likely to get heavier snow now. And the reason is, if it's really cold, we're 0 degrees Fahrenheit or colder, oftentimes there's not enough moisture in the air to produce much snow. You all living in Kansas have experienced this. When it's 0 degrees or less, if you do get snow, it's little tiny flakes that hardly hit the ground. They're blowing along on the wind. The heaviest snows we get are the quote-unquote wet snows right around 30 degrees, near freezing. Almost, part of the atmosphere may be above freezing and part of it is below. And so the more time in winter that we spend right near that freezing line, the more likely you are to have heavy snows. Also, as the climate warms, temperature is directly related to the amount of atmospheric moisture that can exist. And as we warm, so does the humidity. Well, the humidity goes up with that warming temperature. Several years ago, the polar vortex became popular parlance, and everybody said, how can you have climate warming, but you have a polar vortex, which makes it sound like some sort of crazy snow monster thing going on in the North Pole. Again, this is something we understand quite well as climatologists and meteorologists. See if I can explain this quickly. When you have warm air in one area, and I mean like across the southern U.S., and then cold air in another area across the northern U.S. or in Canada, there's a difference in the thickness of the atmosphere. And the thicker parts of the atmosphere, which is shown by this graph, end up having higher pressure at high levels. When you have the colder air, it gets smushed down and it's quite thin, and so the pressures at a particular level in the cold air are closer to the ground. Long story short, you end up with a big, strong pressure gradient going from high to low, and because the Earth spins, that air then turns to the right, well, from your perspective, from high to low, and then to the right. And so in this graph, you'd have wind coming out of the screen. That's the jet stream. That's the wind that flows around the northern hemisphere, and it flows generally in this pattern. If this gradient is really strong, then that wind is screaming, and it's usually in a very tight circle around the cap of the planet, and it's not much waviness. much like a river that's flowing fast downhill mostly goes pretty straight. Rivers that flow slowly over flat areas, they tend to meander. And so when this gradient weakens, you get meandering. And so at the poles, if the poles are anomalously warm, warmer than they normally would be, but still cold, it's still the North Pole, then you weaken that gradient and you start to get waves. And when you get those kinks and waves in the flow, cold air can bleed south, more warm air bleeds north, and you get that variability. Pretty long way of saying we understand the polar vortex. Been around for a long time. It's not new, not made up. It is a process that occurs often whenever you have a anomalously warm polar region. So these are counterintuitive. I understand that. And sometimes it's just overwhelming to people that are not climate scientists to always hear all these ways that climate change relates to their everyday. I understand. I get tired of hearing it sometimes as well. I also get tired of hearing people talk about how meteorologists are bad at their job. But you know what? I keep doing my job. And so that's my next point. What about these climate scientists that can't even predict weather 2 days out, and they want to tell us what the weather's going to be 50 years from now? One, they're not the same thing. People that are forecasting 2 or 5 or 10 days out are typically not climate scientists, and climate scientists typically aren't making forecasts about day-to-day weather. With that being said, the physics that they use is pretty similar. The big picture concepts that they use are pretty similar. And recently, a meteorologist, in full disclosure here, who writes for Forbes magazine, Forbes.com, he does the online stuff, he did a quick analysis of professions that are tasked with making predictions on a regular basis. And he listed a whole bunch, and these are just 3 that I fit on the screen here. One was a stock market analyst. He found that the range of success for stock market analysts, people who predict the performance of the stock market, ranged from about 17 to 79%. These are employed, well-known analysts. These are not your uncle in his basement trying to do some day trading. These are professionals, and 17% was within the range. 79 was the best they could do. Talk show pundits on all the major Sunday talk shows, he could not find anybody better than 50%. And then for meteorologists in the United States, for a 2 to 5 day forecast, we're looking at about 90% accuracy. So this is probably me just getting on a soapbox that may or may not be related. But one, meteorologists are surprisingly accurate. Also, climate scientists and the predictions that they're making, even though their predictions usually are for research purposes and they're designed to test understanding and sensitivity of certain variables to changes, their predictions are becoming remarkably, sometimes frighteningly accurate. And so all of these brightly colored lines here are various climate models. The gray boxes or gray lines shading is the error around our observations, and the black line is our actual observations. And you can see our models, while they are not 100% precise, they're good. They're right on the line. They're helping us understand what's going on. Even our worst models are still within the range of the error bars. So ultimately, if we want to stop hearing about climate change, we're out of luck. It affects a lot. Anytime the climate changes, anytime the weather changes in an afternoon, it affects a lot. People talk about it. That's the way it's going to be. And so this was maybe one of the most sobering pieces of research to come out in the last 5 years related to climate change, and it was from the Pentagon. And it says climate change threatens a majority of mission-critical military bases around the world. This was from Military Times. I mean, this is helping people understand that this is a real threat. And in that report, along with some subsequent reports that came out of the Pentagon, they were talking about that in the future, the military has to prepare not only for infrastructure effects from climate change, but humanitarian effects from climate change. And this was a cartoon that was drawn up to support that conclusion, saying that today, when we have a war, this region of this country, maybe you're going to have refugees, and it becomes a real political question about how to deal with these refugees. Well, instead of being maybe the northeast corner of Syria in future years, it could end up being a 6 or 8 country region across a particular climate area. So the refugees of climate change are likely to be a real thing. There are certainly people already who are seeking refuge in small pockets, but we have to expect that it's going to become larger with time, if we don't do something dramatically to change some of this. So while it does have dramatic effects, and we're likely to feel these for a long time, it doesn't drive everything. Climate change is not the answer to all of our natural disaster-related problems. If you look at hurricanes, somewhat infamously within the last week or two, I believe it was Pence said something along the lines of hurricanes are not increasing, therefore climate change does not exist. Well, he's right, hurricanes are not increasing. That doesn't mean climate change does or does not exist. For decades, hurricane scientists have known we are really consistent in the number of tropical cyclones around the globe every year. Maybe you have more or less in the Atlantic, but if you have less in the Atlantic, you're going to have more in the Pacific. And it has been really consistent year to year. And the data show that. And so these are the hurricanes reaching the U.S. on the bottom, and the orange turning to green line is the total number of hurricanes. We've adjusted it up early in the period because we're sure we missed some. But it's pretty flat. There's noise in it, but it's pretty consistent. And this is just for those in the Atlantic Basin. If you look at the globe, it's even more consistent. We know that. They're not increasing. If you look at tornado data, they are increasing, but it's not for climate change. In fact, we don't even think they're really increasing necessarily. It's just a detection thing. Our radars are better. We have cell phones that we can capture the images of tornadoes. And so if you look at the steep slopes of increasing tornadoes, we don't think that's anything related to climate change. Same with wildfires. Numbers of wildfires generally aren't going up. But we think that we are seeing more impacts from these, and it's not about climate change. It's about people developing more land. So a colleague of mine, Walker Ashley, came up with this concept, or at least he named the concept of the expanding bullseye effect that says, as your cities grow, they're a bigger target. They're a bigger bullseye. And he uses the example in 1950 of if this tornado path, this little cigar black-looking thing here, if it were to hit this city, maybe half the track would be in the urban area, and virtually none of it would affect the core downtown area. As this city grows over time, same track, same location, just with an expanded city, the entire path is within the urban area, and in fact, almost half of the path is in the most developed urban core. So this is one reason that we are seeing more impacts in certain places. But even though we say that these aren't being driven by climate change, they are being affected. It may not be the number one thing, but it's something worth studying and paying attention to. Right now, fire is in the news. It's been in the news for weeks and months, and it's because our fires are unprecedented over the last few years. The numbers, not so much, and not always the size, but it's the intensity and the rapidity with which they form and become intense. And so the total acres burned has risen. The average fire is getting larger. There's other things going on here. There's forest management. There are firefighting policies at play here. But for many decades, those policies worked pretty well. But now climate change is the one thing that's changed in the last few years, 20 or so, and now what we had for several decades is no longer working. So it's not the only thing at play, but it's the thing that suddenly made it interesting. Hurricanes in this case, numbers are not changing, intensity is. The strongest are getting stronger, and they seem to be getting stronger faster. There's also a lot related to the speeds of the hurricanes. As they go more slowly, they do more damage over a longer period. And then there are some tornado effects potentially from climate change. This paper is actually from Todd Moore, new chair in geosciences. And so he showed a couple of years ago that the number of days with 10 or fewer tornadoes is going down, but the numbers of days with 30 or more going up. So again, it's a kind of the worst gets worse, or the bad gets badder, big gets bigger. So we're not having more necessarily, but it's the distribution that's changing, and sometimes in a worse way. Well, some pretty gloomy information that I'm sharing here, and I'll try not to ever end the talk on too much of a downer. And so I wanted everybody to know that one of the best things you can do for your own mental health, instead of just sitting away and letting anxiety grow over climate change, pay attention to progress. Look at the progress that science has made over your lifetime or over your parents' lifetime. This graph on the left is pretty encouraging, and it's from The Economist, and they are showing the blue line is the number of disasters globally, going up dramatically since the 70s and 80s. And it's like I talked about, the cities are expanding, there's more people, and of course there are some more intense events as well. But the numbers of reported deaths are going down. So our economic hit is still there, but lives lost is not nearly what it used to be. So that is progress. Talk about forecasting. This image on the right was from this year. I forget the exact hurricane that it was that was making landfall. Was it Laura, I think, that came in near Lake Charles, Louisiana? Yeah. And so this was the forecast cone for Laura, and you can see it stretches from about Lafayette to Houston. Well, about 10 or 15 years ago, this was a similar forecast from the National Hurricane Center, and you can see the number of days between dots, number of hours, and all is the exact same. It's at about the same spot in the Gulf of Mexico, and what you see is that your cone went almost to Baton Rouge, and then down here to Corpus Christi. More than double the width of that forecast area. Everything is not the same in these two, but I think that's a helpful insight into how we are getting better at this stuff, but it happens gradually. And then, of course, these are kind of fun. This is LAX, the airport in Los Angeles. This is actually from the 1960s, I believe. You can see the old cars. That's the sun. So it's, maybe an hour from sunset. It's still pretty bright, middle of the day type of photo, but all the lights are on, and it looks pretty dark because of the smog. So we have made tremendous progress in terms of pollution and understanding why that's bad. Smoking on a plane, speaking of pollution, same thing. We realize now that's not something that we should be letting people do. It's bad for your health. It's bad for lots of things. So we are getting better. I encourage you going forward to use your BS detectors anytime you see something about climate change. This is a myth now that's been debunked so hard. The people that originally created it have denied that they made it and said the other side made it to make them look dumb or something along those lines. It's really quite silly. But there's still a rumor out there that in the 70s, Time magazine published an issue where the cover had a penguin on it and it said, "We're going into global cooling." And the scientists were all crazy about global cooling. Never happened. There might have been an op-ed piece or two here and there. There might have been an actual research paper or two in the world throughout the 1970s where somebody suggested, we really are cold this decade. If this continues, here's what the future might look like. But nobody actually thought we were going into an ice age. In fact, this was just an issue from about 2007, and people changed the text, and they changed the, here's a MASH ad on the top as opposed to the Sopranos. So that's been debunked many times over. So if you see something and you think, that is unbelievable, I can't believe that they actually did that, and they thought that in the 70s. If you think it's unbelievable, it probably is. Other things that I'm still seeing quite a bit, oh my gosh, with social media, there's so many fake accounts. Twitter is the worst with bots that are programmed with artificial intelligence to give these amplifying responses or maybe combative responses. And you can check that out pretty easily if you're interested in going through the effort. You can check each account, and most of the time the ones that are causing the most trouble are not actually humans. But what this recent research, this is from February of 2020, was that about climate change, on the topic of climate change, about 25% of all tweets came from bots. And 38% of those that were being contrarian about climate change, referring to it as fake science. So more than a third of those were not coming from humans. Conversely, any tweets that were about climate change solutions and activism, they also had their bots, but it was only about 5% prevalence. So you've got to watch out for these. Again, don't believe everything you read or see. This was a petition that, again, came around to me a couple of years ago, somebody asking about it. It is the Global Warming Petition Project. They claim to have over 31,000 American scientists who have signed this, basically saying that climate change is a big fake waste of our time. Well, they did this by asking anybody that has a BS, a University Bachelor of Science, to be eligible to sign it. Anybody with a BS is not necessarily a scientist. They're certainly not a practicing scientist. You could have a BS in lots of things that are nowhere nearly related to science. And suddenly, if you're looking at all people that have gotten their BS in the last few decades, 31,000 is not too many. It's less than 1%. The whole thing was misleading, had absolute impossible phrasing, and they've been adding names since 98, and when people die, they don't take them off. So that's a pretty silly thing that still gets too much credibility. And I thought this was interesting. This was 3 years ago. There was a group of researchers, pretty active climate change researchers, and they did a study of the 3% of science papers that claim that climate change wasn't actually happening. And so you hear that a lot. 97% of all climate scientists or 97% of all climate change papers show that it is a real issue that warrants our effort and our time. There's only about 38 total papers that have been published in science journals that have been able to make reasonable claims that suggest that maybe climate isn't changing like we thought it was. All 38 were shown to have gross statistical errors, so that they could not be replicated. That's the purpose of science. I do this thing, I tell you how I did it, and then you go do it again to show that what I did was actually worth doing and that it made sense. None of those had that ability, so they've all failed that main test of science. Another thing that we're seeing is that we feel like we have to give equal time to anybody that has a different opinion on a lot of topics. Sometimes this makes total sense. If we're talking about, oh, I don't know, putting in a roundabout, yeah, maybe we ought to have a little bit of this side and a little bit of that side. But if we're talking about climate change, where we've already had decades of research and every reputable piece of science that is out there suggests this is happening and this is a big deal, maybe we don't need to both sides that. Maybe we ought to just stop asking the people that are hanging on to these little thin strands to come to the conversation. I equate this to these examples. And so in this case, there was a reputable study that is yet to be discredited that says that if you are a smoker, that lowers your chance of getting Parkinson's disease. And they did a good job with their stats. They controlled for the fact that smokers are less likely to live as long and all these other factors. Still just found out if you smoke, you're less likely to get Parkinson's. We don't know why. But nobody is saying, hey, smoking is bad, you should not do it, it's bad for your lungs, and it's bad for your health, and it's likely to get cancer. But you know, if you don't want to get Parkinson's, maybe you ought to light up. Let's hear from that side. No, we're not doing that. Likewise, this is a story from, I think, within the last year, where this poor kid was in a seatbelt. I think it was one of the automated type seatbelts, and it wrapped around his neck, and according to his mom, nearly strangled him. Well, you know, my grandmother used to tell a story about how she was worried that the seatbelt was going to strangle her, and that's why she didn't wear it. But the rest of us knew better, and thankfully we all continued to wear our seatbelts. This story has not led to anybody coming out and saying seatbelts save lives. However, if you're worried about getting strangled, feel free, don't wear your seatbelt. This is equivalent. This is just like the both sides of climate change at this point. The ship has sailed. There's no reason to deny that climate change exists, and there's very little reason to argue about whether or not it's worth doing anything about. There are valid arguments, though. In that case, it's more of a values thing. But in terms of saying that it doesn't exist, you pretty much lose all credibility in the conversation if you can deny that it even exists. I want to end without being too flippant about some of this stuff. I'm not trying to poke fun, but you don't have to understand it for it to be true. That's the interesting thing about science. That's the interesting thing about having a society. We all carry each other. We help each other out. And so if I expect the scientists to do their jobs, and I'm not a scientist, then maybe I shouldn't try to understand every single thing they're talking about. And when you do, you come in with the improper tools and improper background, you're probably going to make flawed conclusions. Like chemtrails. See this way too much, and I really feel like it's growing. People that think this is a real thing. And so this image on the top left is taken from some sort of chemtrail website, and they're just a photo, I guess it was originally video, of a commercial jet taking off, and they're saying that clearly this is a chemtrail, it's chemicals being sprayed from this plane, and they say you can tell because the spray comes from the entire wing and not just from the engines. So usually condensation trails come straight out of the engines because of the particles and the moisture coming from the exhaust, but not always. When an airfoil or a propeller or anything like that, when it moves through air, it creates a dramatic low pressure right behind it. And whenever you decrease the pressure, you decrease the temperature, and if you're close to saturation, you form a cloud. It's very common. You see it a lot in the winds blowing around tornadoes. This doesn't even have your traditional jet engine, doesn't have the exhaust like you would expect. It's got some, but nothing nearly like a jet. And so what you're seeing are the little clouds being formed on the tips of the propellers. These, obviously not even planes, these are just wind turbines in the English Channel between England and mainland Europe, and you're seeing these clouds forming downstream of the tips of these wind turbines. And so this is the same process. Low pressure, condensation, no chemicals, just clouds. It looks weird. I understand it. I understand that it looks weird. I understand how they form. Everybody doesn't have to. And there's this concept called the Dunning-Kruger effect. Dunning and Kruger are psychologists. Their research led to this graph where they say if somebody knows nothing about a topic, they're very They're lacking confidence. They're very unlikely to comment on that topic. So this is them. Low knowledge, low confidence. But once they learn a little bit, suddenly they think they know it all. And we've all experienced this. We've done it ourselves. We've seen other people do it. You learn a little bit, and you think you have all the answers, and that's this person. Then if they continue to educate themselves, they suddenly realize there's much more going on than they originally thought. And eventually, you might become a foremost expert on the planet, and your confidence will start to rise again, and you'll still be open by saying, we don't know it all. There's things I don't know. It's complicated. Well, this person, the I know everything person, is on this end of the ship and is telling the rest of the ship, they say it's sinking, but we just went up 30 feet. They don't know anything. The captain doesn't know anything. I'll drive the boat. That's climate deniers at this point. They are so well-intended. I truly believe that. They have no idea what they're talking about. All right, well, what do? Just a few slides here. There's no one answer. This is pointing at you. It's pointing at me. It's telling us to not point at each other. If you Google what can I do for climate change, man, there's some consistency, but it's all over the place. Some people say you shouldn't eat as much meat. Well, you know what? Some cultures, meat is a major part. It's not going away. Western Kansas, we're probably not going to stop eating meat, and that's okay. Other places say you need to change your transportation type. Certain people, they're not going to stop flying. You're going to tell folks in Alaska that they can't fly anymore? They'll probably stop eating meat before they stop flying. Trains and public transportation, that's great in a lot of places, but some places it's not feasible. Some folks are saying don't have as many children. Again, that's possible for some folks, not possible for others. There is no single solution. There's certainly not a single solution for everybody or a single pattern for everybody, but there are lots of options that you can do. Some of them are small, things you can do around your house. Some of them take a little more effort, convincing politicians and policymakers to actually do something that makes a difference. The one thing that I want to point out, changing your policies to address climate change doesn't mean you have to go broke. California did a great job of this starting in the early 90s. Even after they implemented their reduction in emissions, their economy continued to grow. It's one of the strongest in the country. It's one of the strongest in the world. And then last slide, Thomas Edison had this quote. He said his goal was to make electricity so cheap that only the rich would burn candles. And I think a lot of us don't want to give up certain things from our culture and our history and our memories, whether that's a gas-guzzling vehicle or if it's a wood-burning fire or, air travel, I don't know, whatever it is that you think you don't want to give up. There were probably people that didn't want to give up candles. Well, we didn't. We just don't rely on them all the time. Candles are still around. We didn't get rid of candles. So maybe if you still want that, that classic car, that will be something that's still around as more of a luxury or a novelty rather than a necessity. And I hear people say, well, I'm not worried about it. Save the planet. Oh, the planet will take care of itself. Nobody actually means save the planet. We may call them tree huggers, but they want the trees there for the oxygen so that we can breathe it. They want to save the planet so that we can live on it. So it really should be save the people. It's not about protecting the dirt. It's about protecting the people that live on that dirt. That is all I have for you. My wife is raising her hand. My son is sound asleep and snoring, so I apologize if you hear that. All right, Melissa, you have a question?
This is a question from the audience. Will climate change be bad for everyone, or will there be winners and losers?
Yeah, like anything, there's going to be winners or losers, and it depends on how we deal with it. And so it is certainly possible, if we do nothing, the people that live along the coast and they're displaced by sea level rise, those will be the biggest losers. Want to be selfish? Living in Western Kansas, you might be a winner in that case. Not a lot of sea rise is going to affect people living in Western Kansas. That's a little bit of a silly response, but yes, almost everything is going to be uneven no matter what we do.
How effective do you feel the mitigation strategies being proposed will stall or slow or reverse the observed temperature changes?
I always try to guess what people might ask and put a slide in at the end to address that. That was the only one I could think of that somebody might ask, and I'm glad you did. These are a lot of the things that we've done over the last 20 years and relative effects that they've had. Some of them that we are pretty proud of, building codes and improved appliance efficiency, U.S. vehicle emission standards. That's quite a bit better than our appliances. They're all still just a drop in the bucket compared to the Montreal Protocol from the late 80s. The best thing that can happen is when countries get together and make a plan to make changes together. And so there is evidence that these things have made huge differences, especially added up all together, but it's going to take cooperation. No single country really can do it on their own. Good question.
Some of the problems of understanding climate change appear to be incomplete understanding or lack of knowledge. What should educators do?
Oh man, I was thinking about that earlier today. If my goal was to undermine scientists, I wouldn't just go out and start talking. Before I undermine experts, I'm going to get together and talk to some people that are experts in communication perhaps, and really refine my strategy and hit them at their weakest spots. But if I'm a scientist, I'm not worried about clever communication. I just share my information because I know it's real and honest and ethical, and I assume that the best stuff will be heard. And that's naive. We now realize that if you're a scientist, you no longer get to be the introverted person in the corner. You have to learn to communicate. You have to come out and be, I don't want to say an activist, but you have to be active and vocal about what it is you're studying. You can't roll your eyes and say, oh, those people don't know what they're talking about. But it's a balance, because nobody wants to be over the top and demeaning and constantly telling people they're wrong. So that's a very challenging situation. But usually the people that plan to deceive have the upper hand early on unless we speak up.
This is the last one I have. How important is this election on climate science?
Oh, I don't know how important it is, honestly. That seems maybe counterintuitive, but there's so much other stuff going on right now. I don't know that we're going to have a lot of climate change legislation in the near term. I told a buddy of mine that works in Western Kansas, works in the energy industry, and he was really curious to know what I thought either candidate might do about climate change. And I said, I hope we find out, because if we start making climate change policy, we will have solved a whole lot of other really big problems in the next couple of years. So I hope it's important for that reason, but I'm not confident.
One more. Does science media literacy have a place in K-12 education, or should we focus elsewhere?
Science media literacy. I don't know. I mean, I don't think the students at K-12, I don't think necessarily need to be taught any more about how to understand reading about science. It's not going to stick with them anyway. I mean, once they get into adulthood and have real jobs and responsibilities, they're going to embrace what is important to them in that moment. I think what's more important is that we restructure how scientists are valued. Maybe restructure how teachers are valued. Scientists right now, they're so interested in a headline type of result or story so that they can amplify their own value and maybe get a better job or get a bigger grant or have something. Scientists are not well paid in this country for the most part. You hear about them getting big grants, but the grants don't pay them. If they do, it's a small amount. And so if scientists aren't feeling pressured to wave their own flag and publicize their own work,